Solving modulus equations. So if you've got an equation with modulus on both sides like this, it's the most straightforward, and there are loads of ways you can do it. You can square both sides, but you can only really do this with ease if you've got a modulus on both sides. So if you square both sides, you're just going to turn it into a quadratic equation. So obviously I've squared both sides, and then I've simplified it. I've divided all through by 3, and unless it says show detailed reasoning, I can just put it in my calculator. I've factorised it, so I've got those 2 solutions. I could have done it graphically. Now, you're massively helped by your graphical calculators in doing it graphically. And what you would then do is you can see that your right-hand solution is where the original bit, y equals 2x minus 5, meets the original bit, y equals x plus 2. So you would just put those equal to each other and you get x equals 7. Your other solution, you've got the reflected bit. So reflected in the x-axis, and you know from your transformations of graphs, you would multiply your equation by -1. So the reflected bit of y equals 2x minus 5 meets the straightforward unreflected bit of x plus 2. So you would put them equal to each other like that and get x equals 1. But either method is great. If you did that same question but with an inequality, because you've got a modulus on both sides, you can square both sides, and that's absolutely great. And the only thing is, you are going to be solving a quadratic inequality. So make sure you do a proper method for that. You know, you get your critical values, but you then do a little sketch to show why you are choosing which bits. So you know that you've got x is greater than 7 or x is less than 1. And again, you could do it graphically, this is more work. You know, I mean, obviously from the previous bit, we know that they intersect at 7 and they intersect at x equals 1. But you want where the modulus of 2x minus 5 is greater than, and it's greater than there, its y values are above the y values of y equals x plus 2, and it's greater than there. So again, you would get exactly the same answer as you had when you did it algebraically. Right. However, if you don't have a modulus on both sides, I would be really wary of squaring both sides. You can, but then you're going to have to check for to make sure all your answers are valid. What I would do if I was solving this is I would do it graphically. So I would sketch y equals the modulus of 2x plus 1. Again, you've got your graphical calculator. So it's going to cross the y-axis at 1. It's going to touch the x-axis at -0.5. I've got y equals 3x, and I can see from my diagram that it's the straightforward unreflected bit of 2x plus 1 meeting 3x. So that's all you would do. Okay, and by drawing the sketch and getting the solution x equals 1, by drawing the sketch, it makes it really straightforward. Here's one that I saw in the textbook and I just thought it was a bit bizarre, so I thought I would do it. So this could happen. This question's from your textbook. So again, I'm wary of squaring both sides, so I'm not going to do it. I'm going to do it graphically. So by now, I've really got the idea. I know there's what the original line would look like, so it gets reflected there. It's going to cut at 1. I should have marked that really, so just imagine that I've marked it there at 1. I then draw y equals 2x. Now you can put these in your graphical calculator. Make sure you know how to get, when you're in graph, how to get the abs up. I think it's on the numeric. You do option and numeric, and that's where you'll get your abs button up to do your absolute value, modulus signs. You know the gradient of y equals 2x is less steep than the gradient of y equals 3x plus 1. So you can see they are never going to meet, but this graph here is always greater, has all that y values are greater than this graph here. So your solution would be all values of x, or if you prefer, all real values of x. This one here. Solve the modulus of x equals minus x. Again, I'm not going to square both sides because one side doesn't have a modulus. I'm afraid of it. So what I've done here is I've drawn y is the modulus of x, which is that sort of V shape there, and then y equals minus x, and you can see that they are overlapping there. So your solution, they are equal when x is less than or equal to 0, where that's basically where they overlap. That would be the solution. And lastly, solve the modulus of x plus k equals the modulus of x plus k. And this is where k is a positive integer. So I know, again, I've done a bit of colour here, the modulus, so y is the modulus of x plus k, looks like that. Then if you think about your transformation of graph, y equals the modulus of x and then plus k, so it's like a translation by the vector 0, k. You can see that they overlap at this bit here. So the solution is x is greater than or equal to 0.